This is an introduction to Newton's second law, the law of acceleration, from Isaac Newton for honors physics. And here we go. This happens to be page 12a, and we're looking at Newton's second law for the first time. So let's examine this. So Newton's second law is all about net forces. Net force means the overall force, or the total of all the forces. Excuse me. It's a little bit like how we use the word net when it comes to banking and finance. Net is the amount of money in your bank account overall. Well, what we mean by that is over the course of a week or a month, if you have a traditional banking account, you have deposits and you have withdrawals. Sometimes those are called credits and debits if you've taken an accounting course or if that's what you're into, right? And so the key idea is that the word net in finance and the word net in physics means look at all the positive quantities, all the negative quantities, all of the quantities that might be in different directions when it comes to vectors. They don't have to deal with vectors in finance, of course. But the key idea here is that the net force is nothing more than the total. It's a vector total of all the forces. That's how we use the word net. The net force is what causes a mass to accelerate. So we use m for mass and a for acceleration. So net forces are causing masses to accelerate. And we write that really as net force equals the product of the mass and the acceleration. Now, I'm going to be writing it not as a net force, but I'm going to be writing it this way, a sigma F, and that means to add up or find the total. I've just noticed over the course of many years of teaching physics that net force somehow doesn't sink in. But when we write it as sigma F, the total of the forces equals the mass times the acceleration, then everyone seems to get it, despite the fact that we're using this Greek symbol that has, abstract meaning. So let's keep going. So there's two conditions that might happen when it comes to analyzing a given mass. Okay, so say you've got a mass and it's sitting on a surface, a table, even the floor. Well, one possibility is that the forces do not add up to zero. The net force causes an acceleration because they are not adding up to zero. The A has some value. Okay. So on the other hand, what if the forces add up to zero? Then the net force does not cause acceleration. And we call that an equilibrium. So an equilibrium is nothing more than when the sum of the forces equals zero. Therefore, the acceleration will also equal zero. Okay? So let me talk a little bit about the part that I skipped in the middle. So you're analyzing motion. Now, there's two ways to be looking at it. You could be looking at the forces. Maybe you know all the forces on the mass, and therefore you're going to predict whether it accelerates or not. Do they add up to zero? Do they not? The other way to analyze motion is to not know anything about the forces, and you just notice that there is an acceleration. Maybe you can see it. So if you can see an acceleration, you can infer that there must be a net force that does not equal zero. You could have a net force that equals zero, but that is not something you can connect to an acceleration. Now, the other way is, as I said, if you know your net force is not zero, you can deduce that there is going to be an acceleration. Okay? So let's kind of talk about how this formula works. And the first time you've seen it is today, or maybe in middle school, but net force is equal to m times a. That's how it's traditionally written in a lot of physics and engineering books. Okay? But we're going to rearrange it because there's a much more convenient way to examine that. And it's right here on the bottom of page 12a. We're going to move the a by itself. We're going to isolate the a. And that's pretty easy. We just have to divide both sides by m. And what you get is a very telling formula. What I mean by that is it tells you far more about how this equation works. So the acceleration of vector, right, is always in the same direction as the net force. And furthermore, if you have a fraction like this, anything on the top is said to be directly proportional to the quantity that's outside the fraction. So the bigger the force, the bigger the acceleration. In fact, it's linear. If you double the force, you will double the acceleration if you keep all other variables the same. Mass, on the other hand, is inversely proportional. And you will see that throughout this year, and maybe you've already seen it in past science, that when a variable is in a denominator of a ratio, an equation, that signals that the larger the mass gets, the smaller the acceleration. So take a truck, pickup truck, family pickup truck. If you put a lot of stuff in the back, a lot of mass, the truck is not able to accelerate the same amount. And you may or may not have experience driving under those conditions. But how about a big dump truck? I drove by a company doing some paving, and they're going to be getting dump trucks full of asphalt. And when that truck is filled with gravel, asphalt, mulch, whatever season it is, whatever product, you have to wait behind it because it just cannot accelerate as much. So the bigger the mass, the smaller the acceleration. That's an inverse proportion. Okay, so let's examine the next page. And that's going to specialize in equilibrium. Okay, so if the sum of the forces adds up to 0, you are in a state of equilibrium. But there's actually two kinds. Okay, you can be at a static equilibrium. So what kind of objects are at static equilibrium? Well, it occurs when the sum of the forces is 0 and your velocity is 0. So maybe you're watching this while sitting in a chair. In which case, there you are, sitting in some kind of chair, and your velocity is 0. We also know that you're not accelerating, probably, in any meaningful way around the room. We also know that your sum of your forces, let's use a new color, your gravity force is matched up and equal and opposite to your normal force. So you're static. Static doesn't mean static cling. Static in physics means not moving. So that's exactly what you're doing. You're at equilibrium and you're static. You're not moving. There's also a different version. There's dynamic. Let me spell that right. Dynamic. D-Y-N-A-M-I-C. Dynamic equilibrium. That's another state where your sum of your forces is 0, but you have a constant velocity. And do you see how that works? It's another case where your net force is 0 and your A is 0, but you're moving along at a steady rate. So if the forces do not add up to 0, the object is, if they're not adding up to 0, the object is not at equilibrium. And we learned that means the system is going to, the consequence is you're going to accelerate the system, right? It accelerates. It's going to change its velocity. Okay, so let's do a few examples. Let's talk about a falling mouse. There was a funny mouse in an elephant slide a few pages ago, but this mouse is falling and there's no air resistance. So let's first analyze what we know. It is definitely experiencing the force of gravity. And there is no air resistance, or at least it's not significant. He's got a very small surface area. He's not falling very fast. That's pretty realistic. There's not going to be much air resistance on a little mouse. So what kind of situation is that? Well, let's draw the free body diagram properly. There's the mouse. Here's the force of gravity. That is not an equilibrium. That object we know is going to accelerate downward at the acceleration that we already know, the free fall acceleration. Now, how about a book? Your notebook, or you're currently holding this sheet of paper on a desk, and it's sitting there, sitting on the table. Let's see, what do we know? If we were to do the free body diagram, it would have the force of gravity on it, and it would have a normal force on it. The table supports the book or the notebook. Well, those two forces, you kind of can deduce that they have to be equal and opposite because it's not falling through the table. So that would be an example of a static equilibrium. Your body sitting in a chair is probably at a static equilibrium. But it's hockey season, or it's getting into the winter, and we've got hockey pucks going across the ice. Captain's practices and tryouts are soon for the Titans team. And let's say you're passing a puck to a teammate at a constant velocity. So let's do the free body diagram for the puck. We've got a force of gravity, and we've got a force normal, and apparently it's pretty frictionless. So all we know, and notice I'm not connecting it, we've got a velocity that's, I don't know, let's make up a number, 8 meters per second. That's about how fast I might be able to push a puck across the ice, assuming I can stand and skate. Not the best, not the worst, but I can do it. And we've got a dynamic equilibrium because the velocity is not zero, but yet the forces are equal and opposite. Into a typical one-dimensional dynamics problem. Dynamics means we're going to be analyzing forces, and consequently, we are going to be predicting what kind of motion is going to be experienced. Is it going to accelerate, or is it perhaps going to have zero acceleration and maintain its velocity? Okay, so you're going fishing, and there's a fish. That's a fish. Yep, that's a fish. And it's being yanked by a fishing line straight up out of the water. Okay. So, right, and then it goes to the fishing pole. So let's do the free body diagram of just the fish. Well, there's a force of tension and there's a force of gravity. Now, for the very first time, we haven't really talked about how to calculate any of these forces or how to quantify them. But in this case, all we know is that there's a tension force of 50 newtons. And because I drew it upwards, that's a positive 50. And I think it was several days ago, we did talk briefly about how to calculate the force of gravity, but the formula is m times g. You take your 3 kilogram fish, and we're going to use, for this problem, for the demo, we're just going to say gravity is about 10 meters per second squared. We could all do it on our calculators. But this fish essentially weighs 3 times 10, or negative 30 newtons. Find the acceleration. Okay, so there is a traditional way of doing this where we did the free body diagram. We chose that up would be positive, down would be negative, and then we're going to use Newton's second law. If you want, you could have done the second law where you add up the forces first and then plug that in. We're going to just embed them right into the formula. So we have a force of tension plus the force of gravity. We're going to do the vector sum, and then m times a. So we have positive 50 newtons plus a negative 30 newtons, and the fish has a mass of 3 kilograms, and the a is the unknown. So 50 minus 30 is 20 newtons positive, equals 3 kilograms times a, and 20 over, I think I misspoke there, 20 over 3 gives you an acceleration equal to 6.7 meters per second squared. And notice it came out positive. That tells you that this fish is going to accelerate quite abruptly up in the air. So maybe he's, the fisherman's sinking the hook, making sure the hook really attaches and the fish doesn't come loose, right? So there's a quick upwards kind of jerk of the line, and it accelerates, okay? Or the fact is, this is a pretty small fish, and that's a pretty big pull, so this thing's going to fly, okay? So that's a typical one-dimensional dynamics problem. You are going to try the next few by either drawing kind of a quick sketch of the object and the relevant free body diagram. So make sure you're labeling all of the forces that are in that picture, and if you know their quantities. So gravity, T, and you'll notice that there's a tension provided. Next step, set up Newton's second law. Then plug in what forces are present in the net force. And from there, you're going to solve for the acceleration. It goes to the bottom of the page. You're going to do one more. Standing in an elevator, the elevator platform, now you know the acceleration. And so you're going to be challenged to find one of the missing forces. In this case, what is the normal force? So thanks for listening and watching, and good luck with your first kinds of problems involving Newton's second law.